the start of another new section of the course, or level 3 on the schedule, concurrency and actors. For this, we want to ask ourselves one big question: how do we write code where multiple things are happening at the same time? How do we write programs that can handle that? So lecture question, you're going to do exactly this. You're going to write one actor class, and we'll, of course, talk about what that is throughout today's lecture. We want one actor class that's going to concurrently track a single int. It's going to take in an initial value in a constructor, and it's going to react to a few different messages. It's going to react to an increment message, which says, increment your value by this much, and then a get message, which says, send me your value, tell me what your value is. And this will be a piece of code that runs concurrently, and then responds to these messages from other code that's also running concurrently. So let's talk about what that is and what that means. Lab activity 5 this week, I want to give a fair warning. It is on the website right now. I want to give a fair warning about what's on it. GUIs and JSON are two topics that you're going to have to use in lab this week. I want to mention this just because those are two topics that I really haven't, we don't really have a lot of practice on. I didn't have a lot of assignments on either one of those. GUIs, I don't think we had a single assignment on yet. We just went over the lecture. So lab will be the first time you are asked to produce a GUI. And JSON, I think we just had one lecture question, if I'm not mistaken. One lecture question, but both of these topics are important for your project demo too. So this lab, I want to use this as bridging a little bit of the gap to project demo 2. You have your choice, just like in project demo 2, between a web or desktop GUI. You're going to get a JSON string, and you're going to have to render it on your GUI. So same thing as with demo 2, just significantly scaled back so it can fit in 2 hours. So just a fair heads up, if you're not comfortable with either GUIs or JSON in either web or desktop, at least study up on one of those and be prepared to write either a web GUI with HTML and JSON, getting HTML and JavaScript, receiving a JSON string, or a Scala GUI using Scala FX and building that GUI, receiving a JSON string, and displaying all those values on the screen. So parsing JSON in Scala, working with Scala FX, parsing JSON in JavaScript, and using web technologies, JavaScript, and HTML to render it. So just a fair warning, the document's on the website. You can look over the whole thing if you want more details. But GUIs and JSON, be ready. So most of what we've done so far in 115 and 116, at least the code that you've written, runs sequentially, meaning that you have a program that's a bunch of lines of code, and each line runs, and then the next line runs, and then the next line runs, and each line is executed in the order that it's written. Then we have a few things. We have some flow control. We have loops where we can run the same lines of code over and over. We have conditionals where we can conditionally run different lines of code. But we're always running one line of code at a time. One thing is happening at one given time, and that's how our programs run, just one thing at a time. So what if we want to run multiple pieces of code at the same time? This is the question we want to ask and answer over the next pretty much all of the next 3 weeks for this whole level. So we've done this before, but we've leveraged libraries to get these tasks done. But in 115, you wrote a web server. Well, what happens when two users make requests to your web server at the same time? Well, if you get two HTTP requests at the same time from your server doesn't just say, well, I'm going to just take one of these, or take them one at a time. Well, it will do them one at a time. But we don't have a clear sequence of code being executed. It's not run this line, run this line, run this line. Instead, you have a web server that's sitting there waiting for requests, and whenever it gets a request, it'll run a certain chunk of code that you give it, and then send a response back to whoever made that request. So we have, last semester you had callback functions that you gave your server and said, hey, whenever you get a request on this particular path, call this particular code, call this function. And then whenever you get these requests, you're calling these functions, and you have no idea what order or how many times or what's going on with these functions. You just know that the server's going to sit there and respond based on the code that you told it to respond with. but no particular order. It's not like running a main method and then this line, then this line. It's here's all the behavior, and then the server just reacts to those incoming requests. We also did this in 1.16. We built GUIs, or at least you will build your first GUI in lab this week. Well, I guess unless you do the web GUI. But anyway, so we saw GUIs. And the GUI is running certain code. It's running our program, and that program, our last GUIs that we made, we're running updates to update movement of shapes. We had some rectangles spinning around. So we had this method, or this function at that time. This function that was being called 60 times a second and updating all of the graphics for our app. And that could have been running a physics engine. I kind of left you hanging at that point where that update loop can be accessing our physics engine and updating all the stuff on the game. But while all that's happening, our GUI still reacted to user input. The user can click the mouse, the user can hit keys on the keyboard, and our program, while updating our physics and our animations and everything, is still listening and reacting to user inputs. And we wrote a few event handler classes. We implemented the handle method, and we said, whenever you get this user input, call this method, do this stuff, run this code. That's happening concurrently with our update loop that's running and updating all our stuff and reacting. And even a user could hit 2 buttons at the same time. Our app's going to react to both of those buttons. I mean, not exactly at the same time. They could be nanoseconds apart or whatever. Enter a queue of events and be handled nanoseconds apart. But for our perception, they're happening at the same time. So for example, Jumper app, we had 2 different players. Player 1 can be hitting a button, left, right, or jump. Player 2 can be hitting a button, left, right, or jump. Both of those button presses can be handled concurrently. We have 2 concurrent players playing our game. So we did concurrent code, but we just leveraged libraries. The libraries did this all for us, whether it be Bottle, our web server, handling it for us, or ScalaFX, JavaFX is our GUI. The library hid all of the concurrency details from us and just said, give me some methods or functions, I'll call them when appropriate, you just write your app, I'll worry about the concurrency. So what if we want to write concurrent code that isn't part of a server, isn't part of a GUI, or just in general, how do we write this code ourselves? How do we not just take what's already out there and just use it? What if we have a custom solution we need to build? What if we want to write custom code, which really, that's why we're here, right? We want to write custom code. We don't want to just use what's already out there. So how are we going to write our own concurrent code and have our own things happening at the same time? And write code where it's not necessarily just one thing that's happening at any given time. We want multiple things happening at the same time. How are we going to do that? And our answer is going to be actors. So in Scala, and particularly the ACA library that we're going to pull in, add to our POM and download, we're going to use an actor system which does a lot to simplify the idea of concurrency. It sets up a structure based on message passing where we can have multiple, instead of thinking of multiple pieces of code or multiple functions running at the same time, we're going to create these actors and have multiple actors running independently of each other. And these actors don't share any data, but they're going to communicate by passing messages. And this is an important part. So they don't share any data, they don't share any memory, because we have this issue that happens when we're running concurrent code. What if I have this code over here running, this code over here running, and this code over here is iterating over a data structure and doing something. For each element in this data structure, I want to do something. Well, this code over here is adding an element to the middle of this data structure or removing an element. What if it removes an element that the loop already got accessed, and now the indices are all off, and everything just gets confused at that point? We have these issues of concurrent reads and concurrent writes whenever we're sharing memory. The actor system is handling this. It's saying, you know what? We're just not going to let you share any memory, so it completely avoids the concurrent read, concurrent write issue. And then if you want to share any information, you have to package that information into a message, send that message off to the other actor, and then you don't get to change that message once you send it. It's not something you can change. Once it's sent, and then we don't have any of those issues with concurrency. If you heard of just general multi-threading, where you have multiple threads running in your machine at the same time, but what if 2 threads are accessing the same file at the same time or something like that? We're avoiding all of that with this actor system. So it's going to do a bit to help us out there. These messages are going to be in the form of case classes and case objects, which is a slightly different type of class or object in Scala. These are mostly used when we don't need any behavior or anything really fancy at all. There's a better way of saying that. But when we don't really need a lot of functionality from a class or an object, and in this case, we're just going to use them to pass these messages. We're going to use a case object when we just need to say, hey, something happened, or hey, this event occurred, or, well, you'll see the usages. But if we just need to send a message with no information contained inside of it, we just need to say, hey, this message. This could be something like hello, there's no information I need attached to that. I just want to say hi to someone. That would be a case object scenario. Case class is when we do want to attach some information to this. These classes typically are only going to have a constructor, and that's it. We're going to have a constructor that stores the value or values that I want to send, and I'm going to send those in messages using these case classes. These give us a few benefits. One is that if we compare 2 case classes or case objects created by case classes, they're not going to be compared by reference. We saw the equals method is always going to compare references for objects. In these case class, built into Scala, will compare them by value. So it'll go to each one of the values from the constructor and check if each one of those are equal, and then do comparisons that way. So things like that, there are other uses for them. We're just going to use them to pass messages. We're not going to worry about the equals and the other properties of these. But suffice to say, they're trimmed down classes and objects that we're just going to use to be able to pass messages. Instead of defining entire classes, having our defining bodies for the class and object, we're just going to keep them simple case class, case object. Now when we have our actor, we're going to see our first actor class here. Actors, to define an actor, that's going to run concurrently in our code, in our programs, we'll create a new class with all the features, everything that we can do with regular classes, except we're going to extend the actor class. This is from the ACA library, so you have to add it to your POM, download the library and everything. We're going to extend actor and then build our class around that, based on that. So we're extending actor and then defining how we react to each message type. I think it's my next slide is the one I'm waiting for. So these types, they're either case objects with no constructor, no values, just a message. And if I have a case object that I'm receiving as a message, I'm going to use this syntax, this receive, and then a case statement, which is going to compare the types and say case, if I get this custom message type that is an object, run whatever code I put here. Just any code that I have, I'm going to put it there, and that's how this actor will react to that message type. If I have a message type that's a class, I can name that variable that I'm getting, name that message, and then access its values while I'm handling that message. So this is the new syntax, and this slide right here is pretty much all of the how to define an actor, what an actor is and stuff. Not too much text on there, but it's going to take us a while to digest this. We'll take it slow, we'll see some examples and see what this means for us. So we're going to extend actor, define our receive, how are we going to respond, to react to different message types. What are we going to do when we get those messages? But this is the crux of it. This is how we define an actor. Then we can create these actors and have them run concurrently in our code. Any questions so far? Okay, so that's defining a class. Now we want to create instances of this class, objects of this new type, and have them actually run concurrently, and we want to be able to pass messages between them. So here's most of the rest of the syntax that we'll use. In our main, this would be our main method effectively, but in our main object, we're going to extend app from the ACA library. Wait, that's not. Oops, that's not right. I mean, that's fine if you think of it that way. But anyway, we're going to create a new actor system. And this system is going to set up all the concurrency that we can add actors to. So we don't just create actors in our program. We're going to create an actor system and add new actors to that system. And then the actors can communicate to each other within this system. When we want to pass a message to an actor, use the exclamation point. That's a tricky one, huh? We're going to use this method in Scala. And I want to take just a brief time out, a little bit of a side message. In Scala, if you ever have a method that takes one parameter, you can call it using infix notation. So here, this is the same as saying actor dot method name parentheses custom message type. It's the same way. Scala just gives us this little shortcut to be able to call methods using an infix notation if they take exactly one argument. Now, for example, int has a method with a name of plus, just the plus sign. That's a method in the int class, so I could say 5 dot plus and then parentheses 6, and then I'll get 11, it'll perform that addition. But we're actually using that infix notation to just say 5 plus 6 to get something that looks more familiar, more of what we're used to looking at. But there's no like special operators in Scala. Even plus, minus, multiplication, those are all actual methods in those classes. There's no special operators. Scala just lets any method with one argument, one parameter, to be called with infix notation. So a little side note, a little thing that Scala gives us. So this library defines a method with this name, and then we're using the infix notation to call it using an infix syntax. You could still call it as a regular method with that name. That's fine too, it still works. But the library kind of pushes this syntax on us. Send to this actor this message. That's the kind of the syntax, the new syntax that we're using here. So notice that we never said new my actor. Question?
So the ACA class overrides the estimation code. Does that mean not or something? Like, does the estimation code mean not?
No, it's in context. So it depends on whatever's to the left of this. You're calling a method named this from that class. So not in, that one does get a little trickier. If it's a Boolean, you can use the prefix notation and put the not before that. But a Boolean has an exclamation point method that you can use as prefix, a prefix method, which I believe prefix, I'm a little fuzzy on this one, I haven't looked it up. But I believe prefix is if it's a method that takes no parameters, you can call it in prefix notation. Don't quote me on that one though. But there is other syntax for other methods. So notice that we never said new my actor. We never said create a new instance of my actor and then just throw it in the system. It's not. If we do that, we're just going to break things. We can't just say create a new instance of my actor. We have to use this props props class of my actor, we want to tell this system, we want to say, hey, actor system, create an actor of this type. So we're going to use this props, which is part of the actor library, class of, which is part of Scala, and the actor of method in the system, the actor system class, to be able to add a new instance of an actor to our actor system. Now, once I run this line, the system is going to create a new instance of the myActor class, a new actor of that type, add it to the system, and return a reference to that actor. And that reference is how we're going to communicate and send messages to this actor. So in here, I have a reference to the actor that was created in this line, and that's how I'm sending a message. I take this actor reference and send it messages. So what if I have, since I'm not saying new and I'm never calling the constructor, we're never calling the constructor for these things. With the previous example, it's fine because the constructor took no arguments. We weren't worried about it. But what if we do have a constructor? We have a constructor in our classes. Remember, these are just a regular class that happens to extend actor and implement this receive method. But a class can have a constructor. It can have multiple values in a constructor. It can have other variables. It can have all this stuff. So what if it has a constructor? We're going to pass that inside of props. So inside the call of props, we're going to add the constructor arguments as an argument list. So the first argument is the class that's going to be instantiated, followed by comma separated, just all of the arguments for its constructor. And now with this syntax, there will be a myActor class created with an input of 10 in the constructor call when it's called. All right, now any questions on this one before we get into a bit more heavy example? Is that at least somewhat making sense? We'll spend a lot of time on actors. I just want to get all the introduction stuff out there. But is this kind of making sense at least? Kind of. I'll take it. This is for what it's worth, this is a tough topic. We are continuing to move through. This is one of those topics that takes a while just to wrap your head around, of multiple things happening at the same time. This next example is our first real example of this, to show that multiple things are happening at the same time, or at least close to the same time. Gets technical, but. Okay, so let's create an example. I want to create an actor that's going to do something pretty simple. It's going to count down from 20 as fast as it can. That's all it's going to really do. I want to create 3 of these and watch them count down simultaneously. Just to show that the concurrency is working, that there are multiple things happening at the same time. So that's what we want to show in this example. These actors are going to react to a few different message types. One of them being the start message, which is going to start the countdown. It's also going to react to it in a question, effectively a question. Are you done? And it's going to respond with a message, whether it's done or not. So let's see this example, starting with the types of messages that we're going to pass. There's actually one more we'll see later that I didn't put on this slide quite yet. But 4 different message types that our class is going to worry about. They're all going to be case objects. We're not sending any data across actors in this example, but we are going to send messages, kind of cues and requests as messages, as case objects. So one message to tell a counter to start, one message to ask, are you done? And then 2 messages, done and not done, that are going to be responses to that question to say whether this counter is done or not, whether it reached 0 from its countdown or not. So we got 4 different message types as case objects that we're going to be passing back and forth, that we're going to be sending across actors. Our class itself, the part I have highlighted here, regular class, this is something we could easily do in kind of in 115, except we have a class and a constructor. But nothing too wild here. I have a class that takes a string as a parameter in its constructor, which is going to, in this case, just be its name. I initialize a variable n to 0, and I have this countdown method that counts down from whatever n is, decrements it until it reaches 0, and then has some print statements throughout the way so we can see how it's behaving and what it's doing. So that, just normal class stuff, with the exception of extends actor, which is highlighted too. Regular class stuff, just a counter class, not much going on. We just want to focus on the actor part of this. So what's the actor part do? So I'm extending actor, which means I have to define this receive. I have to give a definition of this, which is going to say, how does this react to different message types? I'm going to use this case statement. This is all the standard syntax for this library. I'm going to say, when I receive a message of type start, I'm going to reset n to 20 and start the countdown timer. And notice I don't need braces here either. Even though I have multi-line, it's all part of the syntax of the case statement. It's going to wait for that next case to know when to end that code. So reset the timer to 20 and then count down. So I'm saying whenever I receive a message of type start based on this case object start, run these two lines of code, reset n, and start counting down. I have a second message type I can respond to, is done. Whenever I receive a message of type is done, I'm going to respond with either done or not done based on whether I'm done or not. But the key part I want to highlight here is the sender method. So this sender method, this is coming from the ACA library. It's part of the actor class. I'm going to say, send this message back to whoever just sent me this is done message. So when I receive an is done message, I'm going to respond to that sender. I don't care who that sender is. I'm just going to respond to whoever just asked me if I'm done. I'm going to tell that actor whether or not I'm done. And this is how we get two-way communication between actors. This is how we effectively have highlighted here a request and a response, if you want to think of it in terms of HTTP. But we have a method call and a return value, if you want to think about it as methods or functions. But we have a message coming in. I'm going to interpret that message, run the code that I expect for that message, and then send a value back to whoever sent me that message. So if I have an actor doing its thing, doing whatever it does, and then just while it's doing its thing, another actor says, hey, I have a question for you, give me your data or whatever, it can send a message back to that other actor while still doing its thing. So say we have a game running, we have a physics loop running, updating the physics at whatever interval we need, whatever we deem appropriate. It's humming along, doing its thing, moving all these objects, detecting collisions and everything, and in the middle of it, we get a request. Hey, what's the current state of your game? Here's the current state of my game, and I can still keep doing my thing over here. I don't have to, every time the physics updates, broadcast that to everybody or something like that. I can just respond on demand to messages using this actor system. I'll just respond to messages, and I can do those two things at the same time. All right, so let's go back to our actor system with our new class and spin up some of these counters. I'm going to start 3 of these counters. I'm just going to name them 1, 2, and 3. But we're going to create these counters, call the constructor through props like we did before, and then send each one of them using their reference, send each one of them the start message so they all count down simultaneously. So at this point, we have 3 counters counting down from 20, and I'm printing out, where's the countdown method? I'm printing out the name and then the current value of n every time it counts down by 1, and then its name and then finished, just so we can see what's happening with these things. So when I run this code, we have no way of predicting in what order they're going to count down. So we see that the 20s kind of happened all at the same time. 1, 2, and 3 all started their 20 at the same time. But then after that, it's up to the actor system, it's up to our OS, it's up to how the threads are managed, up to how my cores are managed and everything. It's up to a lot of stuff that the actor system, ACM, and everything else isn't going to give us any guarantees about. It's just going to say these things are going to happen roughly at the same time. At least to our perception, it's going to happen at the same time. They all start at 20, and then Actor 2 got some cycles on the CPU. It got to run for a little bit either without the other ones running or while the other ones were really getting spun up or whatever happened. We don't know, we don't care. 1 got to count twice, 2 got to count some more, all the way down to 6. Then 3 finally got a turn, it got some CPU time, and then it just gets mixed up. So we got 3 things happening at the same time, 3 counters going simultaneously. This is what we want, this is what we're looking for. We have 3 things happening at the same time, so if we don't have any specific order that we want things happening in, or we actually want things happening at the same time, or primarily we're listening for user input, we want inputs from the user, but we don't want to have fixed weights in our program. Try to think of how you would react to user inputs in a program that doesn't have concurrency, that has no concurrency. Would you write, okay, update all my stuff, do whatever processing I have to do, and then wait for a bit and listen for user inputs for a little while? And then if you don't get any inputs, go back to computing and then go back to listen for some user inputs. How would you even do that? What if a user clicks while you're computing some physics stuff? It's just not going to work very well. So we need things happening at the same time, and this is how we do it. We have 3 things happening at the same time. We could have 1 actor listening for user inputs, 1 actor updating physics, 1 actor handling AI. We can have these actors doing different things at the same time that don't have any specific order that we need them in. We just need everything to get done. We're going to put each one on a separate actor and let them go.
If you use a debugger on an actor, will it just also go in random order?
That's a good question. That's something we'd have to try. So the question is, if we use a debugger on an actor, you know what? Let's just give it a try. It might pause the whole thing. It's going to be up to the debugger how it's going to behave, though. Put one. Oops, wrong button. So we hit 20, we hit that breakpoint on actor named 1. Let's resume. We hit on actor named 3 at 19. I feel like we skipped something there. 2 on 19. 2 on 17. So it might affect the order quite a bit, but the order is non-deterministic anyway, at least from our perspective. So it looks like it's just stopping at that breakpoint for any of the actors. But it does look like, just anecdotal observation, that it was mixing up the order a little bit. I don't think we had 2 consecutive from the same one yet. 2, it's jumping around a bit more. 1 wasn't at 13. Maybe it is messing up stuff. I don't know. Well, that's something I'd have to look into a bit more. It's possible it completely confused the debugger. But we do get mixed stuff. It's a good question. I want to look into that more now, how it behaves with the debugger. All right, so we have 3 things happening at the same time. Yeah, we're just counting down from 20 right now. It's not very interesting. It's not useful at all. But to prove the point, we do have 3 things happening at the same time. Ish. So, this is an important note. talk about this a bit more as we go on. But when we're thinking of actors, we send two actors off to do things at the same time. We have no idea what order things are going to happen, which brings up important questions of, well, when we're testing, how do we test these? We have actors that depend on each other, and there is some sequence of events that has to happen. How do we handle that? And just being careful of that ordering, knowing that we can't rely on any specific ordering. How do we work around that a bit? So to get that point out there a little more, let's create another actor that's going to depend on the three actors that we already created, and is going to communicate with them using that is-done method. So let's create another one called supervisor, and we're going to start adding in some more of the stuff about classes, data structures, and things like that we already know. So these references that we get here are of type actor ref, which again is part of the ACCA library. So I have these actor references as instances of actor ref, which give me a way to communicate with an actor that's in the system. So the system will give me these references, and it says, hey, if you ever want to send this actor a message, use this reference. And these references can be shared across multiple actors. Multiple actors can have the same reference, and those messages to that reference will go to the same actor. It's similar to a reference in heap space, but it's a reference to an actor in the actor system. So if I have the list of all the actor references that this class is supervising, I can send messages to those actors whenever I wish. So what I want to do is whenever I get the update an update message, which is the new message, I didn't put this on the previous slide, but another case object, this time of type update. And whenever I receive this message, I'm going to send the is-done message to every actor from this list in my constructor. So I'm going to send, in our example here, I'm going to send the is-done message to all three of the counters. When they respond, so I have connected code here, this code, when these messages are sent, I'm going to get a done or not done message back from each of those three counters. So these two pieces of logic are inherently connected, but they're separated through this message passing system. I'm going to send is done. I'm expecting to get one of these two messages back, and I'm going to behave differently, but I have to do this through the message system. So once I send those messages, I'm going to get done or not done, and I'm going to react differently based on the type of message I get. If I get not done, I'm just going to print the counter's not done yet. If I get done, I'm going to add that sender, which sender is an actor ref, and it's going to match the actor refs that I have stored here in this example anyway. But I'm going to add this actor ref to a list of completed actors, and then if that size is equal to the total number, I could have just did counters that size here, but if I have three completed actors, or the code is written in general, it can supervise any number of counters. If I get three different actors that are done, I'm just going to print out all the counters are done. So I'm communicating with those three counters through sending them is done and then receiving the response done or not done. So that's append. So when I did this before, I would do completed equals sender : completed. That's how we would prepend to a list before. I'm using this shortcut similar to when we use plus equals or times equals or any of those. We can use that same syntax here to use the : equals to say add sender to the beginning of this list and reassign this variable to the result. So, and I am starting to sprinkle in more syntax. At this level, I want to start showing off some more of the syntactical tricks. if I could write this in the way that we've seen, in a more familiar way that you've seen in 115, but I want to start showing you some of the, the cooler, more kind of shortcutty things that Scala can do. For example, counters for each. This is same as a for each loop, but I'm calling for each as a method and then running a function on each value in this list. So I take my counters list, and I'm going to say for each counter in this counters list, these are of actor ref, so I'm going to give it a function that takes in an actor ref and just performs some action. In this case, send is done message to that actor. So normally this would take 3 lines of code and a little bit of clutter. The for each method, you can compact it into using for each, a combination of for each and an anonymous function, which is a function that we never assigned, we never gave it a name, why we call it anonymous, but we're declaring the function in line. So we can use the for each method, define a function in line like this based on its input parameters and its body, but doing it in line with this arrow syntax. So some of that stuff I'm going to start sprinkling in a bit more into lectures. But this is the same as for, counter, arrow for in, counters, and then the body of the loop saying counter, exclamation point is done. It would be the same effect, same syntax. Or it's different syntax, same effect. So I'm saying if this sender, this actor ref, is not in my completed list already, prepend it to the beginning of that list, and if the size of my list is indicating that all of the counters are done, print me a message. Now we want to add this supervisor to our system. It takes in as a constructor argument that list of actor references. So I'm going to create a list containing all 3 of my counters. Throw that in the supervisor's constructor, and now I have my supervisor set up to be able to supervise those 3 counters. And this one, we don't really have to worry about this quite yet, not until probably next week. But I'm going to set up a scheduler to send every 500 milliseconds, so twice a second, I'm going to send the update message to my supervisor. So every half a second, I'm going to say, hey supervisor, check up on those 3 counters and see if they're done yet. And then if it receives all the done messages, it's going to say, all right, we're done here. To get this to work, we have to import. This is another one I want to look deeper into to see exactly why this. But we have to import a package from the system variable. So this actor system object that we created, we're importing something from that object. Not 100% sure what's going on, but if you get rid of this line, our scheduler doesn't work. So it's something I'll look into. If somebody does look into it and wants to share, please do. Why that exact syntax is used there. But places to know this has to be here for the scheduler to work. So let's go back to our code and take a look at that supervisor. So we had our 3 counters counting down at different times, reporting when they're finished, but that's just printing to the screen. That's just for our benefit. That really doesn't help our program to know when all 3 of these are finished. But our supervisor can check on them and say, okay, looks like all the counters were finished now. And I wonder if we'll be able to crank this down low enough. Let's just do this. Let's make a quick change here. And update before we even tell these timers to start. Oh, that's not going to work either. Hold on. Let me make another quick change. It's not going to work because I initialized n to 0. So let's initialize n to 1. Just to show the rest of our code working, let's see our supervisor reporting that, hey, these counters are not quite done yet. Let's see if we can get it at least. I think the counters are just counting way too fast. There we go. So counter's not done yet. Like I said, I'm glad I did that because it shows that we can't depend on the order of anything. So even though I'm sending that update message first, I was just hoping that that message passing would outrace the counters, but no, it didn't. In fact, it did not. So I'm sending update to the supervisor, which sends is done to all the counters. By the time is done got to any of the counters, they were already done counting, even though the start message is sent after that update, but this start message ended up being received before the is done message. So that's a good example of we can't, I was hoping to just get lucky there, but that's a good example of how we can't rely on the ordering of anything when we're dealing with concurrent code. Everything can be happening in different order. Just to make sure I'm not going crazy. So if we use, don't do this, I'm just doing this because it's the quickest way I know to get this happening. I did thread.sleep, which just makes this execution sleep for 10 milliseconds, just wait there for 10 milliseconds. That gives the update message enough time to go through, the is done messages time to go through, and then I get the counters not done yet in that 10 milliseconds. But without that sleep, maybe I could refresh it a billion times, and maybe a couple times I might get it happening in a different order. But you know, it's all undefined. It's up to a lot of different variables. Okay, so with that, I'll see everyone Wednesday for the level 2 quiz.